Hi, welcome to Venkatvarma Chemistry YouTube channel. I am Venkatvarma, your host and chemistry enthusiast, here to make your JEE and NEET chemistry easier and more effective. Join us for short, easy to understand videos that cover key concepts, tips and tricks to ace your exams. In this session, I am going to explain alkanes, methods of preparation of alkenes, properties of alkene and chemical properties of alkenes, and some of the exercise. Let's begin our session. Alkenes. See, alkenes mainly saturated hydrocarbons. Alkenes are mainly saturated hydrocarbons are called saturated hydrocarbons. Saturated hydrocarbons are alkenes. See, what is mean by saturated? See, saturated means carbon-carbon single bond. Carbon-carbon single bond is a saturated hydrocarbon. So, carbon-carbon single bond is a saturated hydrocarbon. These are also known as paraffins. These are also known as paraffins. These are also known as paraffins. What is mean by paraffins? These are inert nature of the other substance. Inert nature of other substance like acid, base. So that's why the alkenes are also known as paraffins. Their carbon-carbon single bond, its bond length is 1.54 angstroms. Carbon-carbon single bond, its bond length is 1.54. Carbon with hydrogen, its bond length is 1.12 angstroms. So the bond energy of carbon-carbon, it is a 415 kilojoules per mole. Carbon-carbon single bond, it undergoes sp3 hybridization. It undergoes sp3 hybridization. sp3 hybridization means its bond angle is 109 degrees to 8 minutes. Its geometry is tetrahedral manner. Its geometry is a tetrahedral. See, sp3 hybridization means the percentage of the s character in sp3 is a 25%. 25%. So this is a simple introduction about alkanes. Its general formula is CnH2n plus 2. N stands for number of carbons. N stands for number of carbons. Let's move on. Methods of preparation of alkenes. Methods of preparation of alkenes. See, the first method is by catalytic hydrogenation of alkenes and alkynes. Catalytic hydrogenation of alkenes and alkynes. See, for example, what is the reagent used for the hydrogenation? See, the reagent is H2 gas plus platinum or nickel or palladium metal. Platinum, nickel, palladium metal. Okay, this is the reagent is catalytic hydrogenation of alkenes and alkynes. This is the reagent. For example, carbon-carbon double bond. What it means? It is a alkene. So alkene hydrogenation in presence of H2 gas, or platinum or palladium or nickel metal. What happened? So this breaking of pi bond, keeping of hydrogen. So breaking of pi bond, keeping of hydrogen to form a carbon-carbon single bond. Carbon-carbon single bond is a alkene. See, it means what? Addition of H2 gas. See, addition of H2 gas on unsaturated bond. Addition of H2 gas on unsaturated bond. Unsaturated bond. Yes, let's take RCH double bond CH2 in presence of H2 gas like nickel metal at 200 to 300 Kelvin temperature, the breaking of pi bond, keeping of hydrogen, so it form RCH2 CH3 to form a alkane like platinum, palladium or nickel metal. So nickel metal means at 200 to 300 Kelvin temperature. Sorry, 200 to 300 degrees Celsius. Have a look for next example. See, CH double bond CH2 in presence of H2 gas. In presence of H2 gas like metal, nickel or platinum or palladium. What is? Simply breaking of pi bond, keeping of hydrogen. So CH2 CH3. Have a look for example. C triple bond C H in presence of H2 gas, same environment like nickel or platinum or palladium. It gives what? So simply breaking of pi bonds, keeping of hydrogen. See, CH2. Have a look for next example. CH3, C triple bond CH in presence of H2 gas, same environment. It gives what? CH3, CH2, CH3. Generally, alkanes are more reactive. Alkynes are more reactive than alkenes. Remember, alkynes are more reactive than alkenes. It is an exothermic reaction. In this hydrogenation method, methane cannot prepare. CH4. Methane cannot prepare. Okay. See, let's move on. The second one is reduction of alkyl halide. Have a look for reduction of alkyl halide. What is the reagent? First of all, we can write the what is the reagent used for the reduction of alkyl halide. So what is the reagent? So zinc in hydrochloric acid, okay, or zinc in acetic acid, or zinc plus sodium hydroxide, or zinc copper in ethanol C2H5OH, or aluminium mercury in ethanol C2H5OH. These are the reagents used for the reduction of alkyl halide. Okay, have a look for example. See, alkyl halide formula RX in presence of zinc in HCl. HCl means H plus. So to forming RH plus HX. Okay, see, have a look for example. CH3 CH2Cl in presence of zinc in H plus, zinc in HCl. What is a product? CH3 plus HCl. reduction of alkyl halide to alkane, ethyl chloride to ethane, ethyl chloride to ethane, ethyl chloride to ethane. Have a look for next example. See, in this CH3, CH2, CH2, Cl in presence of zinc in HCl, H2 gas, it gives propane CH2, CH3 plus HCl. Yes, now generally the reducing agent lithium aluminum hydride also used for this method. So primary and secondary, alkyl halide, primary secondary alkyl halide in presence of lithium aluminum hydride, it gives a primary secondary alkane, primary secondary alkane. In tertiary alkyl halide there is no reaction with alkane. So in tertiary alkyl halide used in lithium aluminum hydride, it gives alkenes, not gives the alkanes. Okay, primary secondary gives alkanes, tertiary we can use to give alkenes. For example, CH3, CH2, Cl, what is the reagent? Lithium aluminum hydride, it gives what? Alkane, CH3, CH3. If use tertiary alkyl halide CH3, Cl in presence of lithium aluminum hydride, lithium aluminum hydride, it gives what? Alkene, alkene means it is a 2-methyl propene, 2-methyl propene, it is a alkene. Yes, have a look for next example. See, if in presence of secondary tertiary alkyl halide in presence of sodium borohydride, it gives secondary tertiary alkane, secondary tertiary alkane. If use primary alkyl halide in presence of sodium borohydride SBH, it's no reaction, no reaction with primary alkyl halide. So if use hydrogen iodide, red phosphorus, hydrogen iodide and red phosphorus is used, just X remove means halide remove and adding hydrogen, hydrogen iodide red phosphorus is used, just X remove, X stands for halide remove and adding the hydrogen. Yes, for example, we can use primary, secondary, tertiary alkyl halide, in presence of triphenyl tin hydride. What is the reagent? TPH, triphenyl tin hydride. It gives primary, secondary, tertiary alkane, primary, secondary, tertiary alkane. What is the reagent? TPH, triphenyl tin hydride, triphenyl tin hydride. This is for the reduction of alkyl halide, Have a look for next method. See, Woods reaction. What is Woods reaction? See, Woods reaction is a formation of carbon-carbon bond formation. It is a carbon-carbon bond formation, Woods reaction. Generally, alkyl halide. So 2 moles of alkyl halide in presence of sodium dryether, to give alkane, See, here what happened? Breaking of bond to form a free radical. So 2 alkyl free radical to give the alkane. It is a preparation of even number of alkanes. Woods reaction, it is a preparation of even number of alkanes, not for odd. Okay, so it is easy to write the product. For example, alkyl halide in presence of sodium diether, 2 moles of alkyl halide, 2 moles of alkyl halide. So simply see Primor law of 2NaX. So adding these two RR and 2NaX. 2NaX. In this Woods reaction involved free radical mechanism and ionic mechanism. Ionic mechanism. Free radical and ionic mechanism. I will look for example. See CH3 CH2Cl in presence of sodium with the Cl CH2 CH3. What is the product? Very simple. So this is a product to form a butane CH3 CH2 CH2 CH3 plus 2 NaCl. This is for even number. Butane means 4 carbons. It is the best method to preparation of even number of alkenes only. If use we are taking same type of alkyl halide. If different types of alkyl halide, what happened? To give mixture of alkanes. To give mixture of alkane, that is a crossed Woods reaction. That is a crossed Woods reaction. See, taking two different types of alkyl halide. Two different types of alkyl halide. See, crossed Woods reaction. Different types of alkyl. For example, RX with the sodium and dry ether. See R dash X. See, wait. See, R dash alkyl halide. So it gives what? See, the first one, it gives R dash, one type of alkene, R one type of alkene, and R dash and R dash. It gives mixture of alkenes. It gives mixture of alkenes. If I am taking one example for this, see for example CH3 Br plus 2Na plus Br C2H5 in presence of dry ether. In presence of dry ether. See, it gives what? See, first of all, CH3, CH3, C2H5, one type of compound. See again, CH3, one type of mixture. See, C2H5, one type. So it is a mixture of alkane. It is a mixture of alkane. So it is not best method for the preparation of alkenes. Why? Because of this is a mixture of alkenes. The boiling point is very near boiling points, methane, ethane and butane and propane. So these boiling points are very near, not easy to separate them. So that's why it is a not best method for the preparation of alkenes in crossed Woods reaction. Crossed Woods reaction. Let's take one more example for this. See, if I am taking for intramolecular Woods reaction. See, intramolecular Woods reaction. What is a intramolecular Woods reaction? Let us take example. See, this is a alkyl halide in presence of sodium in dry ether. In presence of sodium in dry ether, it gives what? Cyclopropane and sodium bromide. Sodium bromide. Sodium bromide. It is a intramolecular Woods reaction. Intramolecular Woods reaction. Okay. See. Have a look for next one. Woods fitting reaction. Woods fitting. In this Woods fitting reaction, see alkyl halide with sodium dry ether with aryl halide. Alkyl halide, aryl halide. Sodium in dry ether. Sodium in dry ether to give alkyl aryl. Alkyl aryl and sodium halide. So, for example, methyl chloride with sodium dry ether with chlorobenzene. Chlorobenzene. It gives what? It gives what? See, simply toluene is given and sodium chloride. This is for Woods. Means one alkyl halide, one aryl halide in presence of dry ether to give alkyl aryl or alkyl benzene. Alkyl benzene is formed. It is a toluene. It is a toluene is formed. Have a look for next one. Fitting reaction. What is fitting reaction? In this fitting reaction, taking 2 moles of aryl halide. 2 moles of aryl halide in presence of sodium in dry ether. In presence of sodium in dry ether to give biphenyl. To give biphenyl and sodium halide. It is a biphenyl or diphenyl. Biphenyl or diphenyl. Have a look for next question. See, Ullmann reaction. What is Ullmann reaction? Same aryl halide. So 2 moles of aryl halide. 2 moles of aryl halide in presence of copper in dry ether. In previous we are using sodium in dry ether. That is a what reaction? Fitting reaction. In Ullmann reaction we are using the copper. So here also form biphenyl. To form a biphenyl and copper chloride or copper halide. CuS. Copper halide. Okay. This is for Ullmann reaction. Ullmann reaction. See, next one. Franklin reaction. Next is the Franklin reaction. What is Franklin reaction? It is same as Woods reaction. It is the same as Woods reaction, but one difference is there. Instead of sodium, we can use zinc. See, same situation. Alkyl halide with zinc in dry ether. To give alkyl and zinc halide. It is a Franklin reaction. Have a look for next reaction. See, Korehouse synthesis. What is Korehouse synthesis? The preparation of alkanes, symmetrical and unsymmetrical alkanes prepared by using Korehouse synthesis. It is also one of the best method for the preparation of alkanes. So the reagent is lithium dialkyl cuprate is a Gilman reagent. The reagent name is a Gilman reagent. What is Gilman reagent? Lithium dialkyl cuprate is a Gilman reagent. See, in this Gilman reagent also formation of new carbon-carbon bond formation. New carbon-carbon bond formation. See, in this choreo-synthesis, alkyl halide with lithium to form a alkyl lithium. Alkyl lithium with a copper iodide to form a dialkyl copper iodide and lithium iodide. So again dialkyl copper iodide with another alkyl halide. It gives alkyl R and R dash with it form R and R. So the Corey-House synthesis mainly symmetrical and unsymmetrical. Symmetrical and unsymmetrical both can be prepared. Both can be prepared by this method, Corey-House synthesis. The reagent is Gilman reagent. I will look for next method. The next method is decarboxylation. What is meant by decarboxylation? Very simple. Removal of carbon dioxide from salt of carboxylic acid. See, decarboxylation or from carboxylic acid. See, sodium salt of carboxylate ion or COONA in presence of soda lime. Soda lime means NaOH plus CaO. It is a soda lime decarboxylating agent. So simply removal of COONA. Adding of hydrogen. See, removal of COONA, adding hydrogen or addition of hydrogen to form a RH. Yes, plus sodium carbonate Na2CO3. So this is having one carbon is less than parent compound. See, one carbon is less than parent compound. One carbon is less than parent compound. Yes, I am taking one example. So CH3COONA in presence of soda lime NaOH plus CaO. Very simple. So removal of CONA, adding of hydrogen CH4 plus Na2CO3. Yes. See, I will look for one example. See, COONA with soda lime NaOH plus CaO. So simply breaking of CONA, adding of hydrogen. See, it gives propane. Yes. See, this is for decarboxylation. I will look for next method. See, the next one is coal-based electrolysis. Coal-based electrolysis also formation of new carbon-carbon bond formation. See, it is same like Wurtz reaction. If I am taking salt of carboxylate ion, sodium salt of carboxylate ion like RCOONA or RCOOK, sodium salt of carboxylate ion or potassium salt of carboxylate ion. See, I am taking R COOK plus or COOK, potassium salt of carboxylate ion. Electrolysis in presence of water. Electrolysis in presence of water. It gives what? Alkene. It gives alkene and carbon dioxide. What next? H2 gas and potassium hydroxide to form a potassium hydroxide. See, alkene and carbon dioxide, alkene and carbon dioxide at anode and H2 and potassium hydroxide at cathode. Released anode it formed the alkene, cathode at H2 and potassium hydroxide. See, if I am taking salt of carboxylate, potassium salt of carboxylate, electrolysis, very simple, breaking of bond to form a free radical and alkyl free radical again to form a alkene, Yes, if I am taking C2H5 COOK, electrolysis, it forms what? C2H5 and the C2H5, it gives what? CH3, CH2, CH2, CH3. It is a N-butane to form a N-butane at anode during electrolysis process. Yes, this is about coal-based electrolysis. It is same as Wood's reaction. Yes. Move for next reaction. See, Clemmensen reduction in presence of acid medium or acidic medium. So, very simple, aldehyde or ketone in presence of zinc amalgam with a concentrated HCl, it gives what? Alkene. Very simple. So, the carbonyl compound is converted to alkene. See, same as aldehyde RCHO to form a RCH3. Again RCOR to form a RCH2. Or carbonyl compound is converted to alkene. That is a Clemmensen reduction. Have a look for next one. Wolff-Kishner reduction. What is Wolff-Kishner reaction? See, NaNH2KOH glycol or sodium hydroxide. See, same as aldehyde ketone in presence of NH2 hydrazine, NH2 sodium ethoxide, it gives alkene. This is for Wolff-Kishner reduction. Wolff-Kishner reduction. See, have a look for next method from Grignard reagent. What is Grignard reagent? Alkyl magnesium halide is the Grignard reagent. RMGX. Alkyl magnesium halide is the Grignard reagent. See, how to prepare the Grignard reagent? See, alkyl halide with magnesium dry ether to give alkyl magnesium halide. So like R minus Mg2 plus X minus. See, this R minus with a big hydrogen H plus It is a acidic hydrogen. Acidic hydrogen. It gives alkane. It is a alkane. So it is a method for preparation of alkane. In presence of carbon ion means or minus with in presence of acidic hydrogen, it gives alkane with MgOH. I am taking one example for this. See, alkyl magnesium halide or MgX with H2O like water H2O. It is also having the acidic hydrogen to give alkane. Yes, and in presence of ethanol C2H5OH, it is also having the acidic hydrogen to form a alkane. Again, carboxylic acid or COOH, it is also having the acidic hydrogen to form a alkane. Yes, and acetylene HC triple bond CH, alkene to form a alkane. In presence of acidic hydrogen, alkyl magnesium halide, it gives alkanes. It gives alkane. This is for Grignard reagent used for the preparation of alkanes. So how to prepare the Grignard reagent? Alkyl halide with magnesium dry ether to give alkyl magnesium halide. This alkyl magnesium halide with acidic hydrogen to give a alkane. Yes. Now next one. Very simple. RMgX in presence of H2O, acidic hydrogen. It gives what? It gives CMgOH. What is the remaining? RH. Okay. Like alcohol, like ROH. It gives what? Alkene. It gives alkene. Next method, hydrolysis of carbides. Hydrolysis of carbides. Next one is the hydrolysis of carbide like aluminium, beryllium carbide. So aluminium and beryllium carbide hydrolysis, it gives alkane. For example, aluminium carbide, so Al4C3 hydrolysis H2O, and beryllium carbide Be2C, so it is 4 minus in presence of H2O. Hydrolysis, so both are giving what? Methane. Both are giving a methane. So it gives aluminium hydroxide, and it gives what? Beryllium hydroxide. Aluminium carbide, beryllium carbide to produce alkene. See, beryllium carbide. These are the methods of preparation of alkanes. See, have a look for the next one is physical properties of alkane. See, have a look for physical properties of alkane. What are the physical properties of alkane? See. Generally, physical properties are there C1, C4. So C1 to C4, they are gases. Alkanes are gases. C5 to C17, they are liquids. Above C17, they are solids. C1 to C4 gases, C5 to C17 liquid, and above C17 are solid. Have a look for solubility of alkanes. Generally, alkanes are non-polar. See, alkanes are non-polar nature. Insoluble in water. Yes, insoluble in water. Alkanes are non-polar. They are insoluble in water, soluble in non-polar solvents. So soluble in non-polar solvents. What are the non-polar solvents? Non-polar solvents like benzene, carbon tetrachloride. Benzene carbon tetrachloride. Yes. Have a look for boiling point of alkane. Boiling point of alkane is directly proportional to number of carbons. Boiling point is directly proportional to number of carbons for alkanes. For alkanes. Yes. Boiling point of alkenes is directly proportional to number of carbon atoms. Number of carbon atoms. See, boiling point is directly proportional to molecular weight of alkenes. Boiling point is directly proportional to molecular weight. Yes. So, what is boiling point is directly proportional to molecular weight. So, if van der Waal, see, van der Waal of van der Waals of attraction, van der Waal of attraction is directly proportional to molecular weight and directly proportional to surface area. Surface area. Surface area of molecule. Surface area of molecule. See. Van der Waals of attraction is directly proportional to molecular weight and directly proportional to surface area of molecule. See, I am taking boiling point of, boiling point of, 1, 2, 3, 4, 5, pentene, N pentene, 1, 2, 3, 4, 5, 6, N hexane, 1, 2, 3, 4, 5, 6, 7, it is a pentane. Yes, N pentane, N hexane, number of carbon 1, 2, 3, 4, 5, 6, and N heptane. Number of carbons increases, boiling point increases. Boiling point increases. Yes. Now, boiling point is inversely proportional to number of side chain. Number of side chain. It means what? Branching. Branching. It means what? Branching. Branching increases, boiling point decreases. Okay. Have a look for example. See. See, it is a 1, 2, 3, 4, 5 N pentane, methyl butane, and 2 gamma 2 dimethyl propane. So, which has highest boiling point? Obviously, the first one is more because of 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. All are having same number of carbons. Yes, same number of carbon atoms, same number of carbon atom, but branching is increases. Branching is increases means boiling point decreases. Why it decreases? Because the shape approaches. See, the shape approaches to spherical. The shape approaches to spherical, which results in decreases van der Waal forces. Van der Waal forces and decreases van der Waal forces. So boiling point will be decreases. Okay. See. Chain isomers are more branched, less boiling point. More branched is a less boiling point due to minimum surface area, and weak intermolecular forces. Yes, these are the physical properties of alkenes. I will look for next one. Chemical properties. Chemical properties of alkanes. Chemical properties of alkanes. See, in chemical properties of alkane, the first one is halogenation. See, in chemical properties, the first one is halogenation. Halogenation. During halogenation, see, what is the reagent used for the halogenation? Halogen in presence of H nu, X2 in presence of H nu, UV light. So simply remove hydrogen and add halogen, add X. For example, alkene RH in presence of HX in presence of H nu, simply remove X2, remove HX, it gives RX and plus HX. This is for halogenation. For example, methane in presence of chlorine, H nu, it gives methyl chloride and HCl. Okay, this is for halogenation. I will look for next one, isomerization. What is mean by isomerization? So, what is the reagent used for the isomerization? Anhydrous AlCl3 and HCl, hydrochloric acid. Generally, isomerization means N-alkane to branched alkane. What is mean by N-alkane? Normal alkane to branched alkane. What is the reagent used for the isomerization? Anhydrous AlCl3 HCl. Anhydrous AlCl3 HCl. For example, butane CH3, CH2, CH2, CH3. It is a N-butane. Yes, N-butane, normal butane. So the reagent in presence of anhydrous AlCl3, it gives isobutane. It gives isobutane. So it is a N-alkane, normal alkane. It is branched alkane. It is isobutane. Isobutane what? It is a branched alkane. Yes. See, have a look for example. See, I am taking hexane CH3, CH2, 4CH3 in presence of reagent anhydrous AlCl3 and HCl. What is the product? See, it gives CH3, CH3, CH2, CH2 and CH3. 6 carbons. Have a look for next one. CH3, CH2, CH3, CH2, CH3. It gives 1, 2, 3, 4, 5. See, 1, 2 methyl pentane. It is 3 methyl pentane. 2 methyl pentane, 3 methyl pentane. Both are branched. So normal alkane to N-hexane to branched alkene, 2 methyl pentane and 3 methyl pentane. These are the isomerization. This is the isomerization. Have a look for next property, Aromatization. The next one is aromatization. What is aromatization? What is a reagent used for the aromatization? See, oxides of chromium or molybdenum in presence of Al2O3 to give N-alkene 2 aromatic ring. So N-alkene 2 means normal alkene 2 aromatic ring. Normal alkane 2 aromatic ring in presence of Cr2O3 Al2O3 at 500 degrees Celsius. For example, N-hexane. I am taking N-hexane in Cr2O3 Al2O3. It gives C6H6 benzene to release the H2 gas. To release the H2 gas. This is what is the environment? 10 to 20 atm pressure. Cr2O3 Al2O3. Okay, or 773 Kelvin temperature. Have a look for N-heptane. N-heptane in presence of Cr2O3 Al2O3. It gives toluene C6H5CH3 and release 4H2. It is a toluene. It is a benzene. It is a benzene. N-hexane to benzene. Toluene to, sorry, N-heptane to toluene. This is the aromatization. This is the aromatization. Next is the nitration. Nitration. See, what is the reagent? Concentrated HNO3. Concentrated nitric acid. See, alkene in presence of concentrated nitric acid like HO plus NO2, HNO3. Yes, so it form RNO2, nitroalkene, like methane. For example, CH4 in presence of HNO3, 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 it gives CH3NO2, CH3NO2, nitroalkene. Yes, next, sulfonation. It is for nitration. Next for sulfonation. So sulfonation, alkene in presence of concentrated sulfuric acid like H2SO4, HOHSO3, simply, or SO3H or SO3H at 400 degrees Celsius. Sulfonation. This is for sulfonation. Have a look for next combustion reaction. Combustion, oxidation. See, oxidation is controlled oxidation. Controlled oxidation means passing of limited oxygen. See, CN H2N plus 2 plus 3N plus 1 by 2 O2 gives rise to NCO2 plus N plus 1 H2O. Combustion means alkane in presence of oxygen. Burning to release carbon dioxide and water is a combustion reaction. Yes. For example, in partial oxidation, methane, partial oxidation in presence of O2, heating in presence of nickel, steam at 1000 degrees Celsius, it gives CO plus H2, carbon monoxide and hydrogen. Methane with oxygen, copper at 200 degrees Celsius. It is a partial oxidation. It gives methanol, CH3OH. Again, methane combustion in presence of molybdenum oxide at 200 degrees Celsius, it gives formaldehyde. It gives formaldehyde. Again, see, presence of potassium permanganate. Potassium permanganate. See, oxidation. It gives tertiary butanol, 2-methyl, 2-propanol. It gives alcohol. It gives alcohol in partial oxidation. Control oxidation. Next, complete oxidation. Going to complete oxidation. In complete oxidation, methane in presence of oxygen, to release carbon dioxide, water. Carbon dioxide, water. Okay. Again, ethane combustion, C2H6, combustion in presence of oxygen. It gives carbon dioxide, water. This is for complete oxidation, to release carbon dioxide, water. We look for pyrolysis or cracking. Pyrolysis or cracking, it is higher alkene, higher alkanes in presence of high temperature like 973 Kelvin temperature. It gives lower alkanes. It gives lower alkanes. At higher temperature, it gives lower alkanes. For example, 773 Kelvin temperature, higher alkene, I am taking example C6H14. C6H14 in presence of 773 Kelvin temperature. 773 Kelvin temperature, it gives C6H12 plus H2. Again, C4He8 and C2H6. Again, C3H6 plus C2H4 plus CH4. Lower alkanes. It gives lower alkanes. The pyrolysis process. Higher alkane to lower alkanes. The decomposition of higher alkanes to lower alkanes in presence of higher temperature. The process is known as pyrolysis or cracking. Pyrolysis or cracking. These are the methods of preparation of alkenes and properties of alkene and chemical properties of alkene. See, next is how to find out major product in monochlorination process. It is very important for the JEE and NEET examination. How to find the major product in monohalogenation process. See, have a look. chlorination, bromination. During chlorination and bromination, in chlorine, more reactive, less selective nature. Chlorine has more reactive, less selective. Bromine, more selective, less reactive. Chlorine is more reactive, less selective. Bromine, more selective, less reactive. Yes, the reactivity of primary hydrogens, the reactivity of secondary hydrogen, and reactivity of tertiary. So it is a ratio 1 is to 3.8 is to 5. Okay. In bromination, reactivity of primary, reactivity of secondary, and reactivity of tertiary. Okay. See, it is a 1 is to 82 is to 1600. So how to find the major product? By using percentage of the primary and percentage of the secondary. So we are taking percentage of the primary equal to number of primary hydrogens and reactivity of primary divided by number of primary into reactivity of primary plus number of secondary and reactivity of secondary plus number of tertiary and reactivity of tertiary into 100. This is a principle to find the percentage of the compound. Percentage of the compound. NP stand for number of primary hydrogens. NS number of secondary hydrogen. NT number of tertiary hydrogen. Remember this, the reactivity of chlorination 1 is to 3.8 is to 5. Reactivity of bromination 1 is to 82 is to 1600. Have a look for example. See, if I am taking N-butane chlorination, it gives 1 chlorobutane and 2 chlorobutane. Chlorobutane. See, 1 chlorobutane is 28% and 2 chlorobutane is 72%. How to decide whether it is a minor, it is a major? By using this principle. See, if see, I am taking see, if primary percentage of the primary number of primary hydrogens present in the N-butane, so it is a primary, it is a secondary, it is a secondary, it is a primary. Primary hydrogens are 6. Reactivity of primary hydrogen is a 1 divided by number of primary, yes, and number of secondary. So number of secondary is a how many secondary? 4 is into 3.8 into 100 into 100 becomes 6 divided by 6 plus 15.2 into 100, it becomes 28% nearly. Okay, have a look for percentage of the secondary. Percentage of the secondary means number of secondary hydrogens and reactivity of secondary hydrogen divided by number of secondary reactivity and number of primary and reactivity into 100. Yes. So number of secondary hydrogens are 4 into 3.8 divided by 4 into 3.8 divided by number of primary is a 6 and reactivity of primary 1 into 100. Here becomes what? 15.2 divided by 15.2 plus 6 into 100, it becomes 72%. 72%. See, this is a way to calculate the percentage of the compound, which is major, which is minor. See, have a look for next. Next is how to find number of products in monohalogenation process. Number of products. For example, methane is there. Methane halogenation, it gives methyl halide. Methyl halide, it gives only one product. Yes, it gives only one product, methane. Ethane halogenation, it gives ethyl halide. It is also giving one product. Yes. Now, propane. Propane halogenation, it gives two products. It gives two products. One chloropropene and two chloropropene. See, have a look for next example. See, it gives N-butane. N-butane halogenation, how many products are formed? See, I am writing the products. See, A plus 1 halobutane or 2 halobutane or 1 chlorobutane and 2 chlorobutane. See, it is a 1 in this 2 halobutane. It has one chiral center. See, chiral center. The excluding stereoisomers. Including stereoisomers are 2. Including stereoisomers. See, including stereoisomers are 3. So it is a chiral center to form a 2 isomers. It gives 1 isomer, it gives 2 isomer. So 1 plus 2, it is a 3 isomer. Including isomers are 3, excluding isomers are 2. Yes. So total number of monochlorinated products. See, total number of monochlorinated products. Total number of monochlorinated products are 3. Yes. Enantiomer pair. How many enantiomer pair? Enantiomer pair is only one enantiomer pair. Yes. So enantiomers, how many enantiomers possible in N-butane? 2. Enantiomer pair is 1, enantiomers are 2. So number of products, important, number of products separated by fractional distillation. Number of products separated by fractional distillation is 2 only. Yes. Number of structural products. Next is the number of structural products are 2. Number of structural products are 2. Number of chiral products are also 2. Number of chiral products are 2 for N-butane. For N-butane. See. Have a look for next example. Have a look for next example. See. See. Next one. See. How many of the isomers are possible excluding isomers and including isomers? See, excluding isomers are 4 and including isomers are 6. So I'm explaining about this example. See, if this is a halogenated center 1 and 2, yes, 3 and 4. So in this center has chiral center, yes, in this it is a chiral center. Chiral center means possible 2. So here also one chiral center is there. Here also possible 2 and 2. See, 4 and 5 and 6. 5 and 6. I am writing isomers. See the first one. Product. Yes, I am writing second one. It is a chiral center. It forms 2 products. Yes, again this one. Use 1 product. Again next one. Adding halogen H, it is a 1 chiral center, so it gives 2 products. The total is excluding is the 4. 1, 2, 3, 4. So including isomers, stereoisomers are 6. So here possible 2, 2 plus 2, 4, 5, 6. Possible excluding isomers are 4, including isomers are 6. Have a look for next example. Possible excluding and including. See. Example, chlorination. Yes, monochlorinated products. Monochlorinated products are only 1. Excluding isomers are 1. Isomers are 1 only. This is about finding of monohalogenated product. This is a complete alkanes. See. Yes. If video is helpful, please subscribe the channel and hit the bell icon to stay update the latest videos and notifications. Thanks for watching.